me just check that my mouse works.
It does. It looks like it does.
Okay, goody.
Should I go?
Are we?
All
I'm
right,
just-
seniors.
Are we in frame? Are we?
Uh,
I don't think all three of us are going
Either,
to be
I
in
think only one currently visible.
Yeah.
Okay, Hannah, you're on.
I'm kind of in frame. There's
Barely.
three of us
Your
here.
arm is. Yeah, we're all here.
Good morning,
How are we
seniors.
moving it?
I'm
I
so
can do
glad.
I have my mouse. Yes.
Okay, perfect.
I'm
Okay.
so I'm
Oh.
so glad you're doing this for your capstone project. It's awesome. We see you, but
Okay.
Okay, here we go.
I want you
Great.
to just introduce yourselves and I know you're all seniors, so just tell us what your plans is after high school here.
My name is Reese, and I want to go to college for mechanical engineering.
Awesome, Reese.
My name is Hannah. I'm also planning to go to college for mechanical engineering.
Awesome.
Hi, I'm Keshav. I want to pursue material science with a focus in energy sustainability.
Wow. Wonderful. Okay, we see your PowerPoint, so you can proceed.
All right, so obviously we're doing the lunar sample box, and we already introduced ourselves, so if you want to skip by.
So some of the design constraints that we were focusing on when making our prototype was the weight, the extreme temperatures, and especially the charged glass shards that could affect the seal. Also the usability, especially with like the big gloves that astronauts would use, the transportability, the size, and just the constraints around having an object in space.
Wrong way. This was just the start of our brainstorming process. We thought we'd throw that on there.
And then after that, we moved on to like sketches of our idea. So we wanted to do something cylindrical because we thought it'd be the strongest shape and it's condensed. So we'd be able to fit the baseball sized rocks in it, but it wouldn't take up a huge amount of space. And then we also wanted to do some sort of like hexagonal shape on the outer part of the container so that it'd be easier to like hold on to and move around versus just having a smooth like outer face. And then on the inside, we wanted to have spring energized seals as a measure of protection against leakage with microfiber like piece on cloth on the top to wipe away the dust as the cylinder gets pressed down onto the outer cylinder gets pressed down onto the inner cylinder. And then we also wanted to have O-rings at the top and bottom as like an extra layer of redundancy to help prevent leakage.
So to illustrate that best, we made this prototype here. I'm just going to use the camera if you don't mind, because I think it's a little easier to see.
Can you just click over to the camera? I don't want to stop the sharing in case it breaks.
Can you see the camera?
Yeah, I can do that. Go ahead.
Okay, so this is our current prototype here. We wanted to add a handle so it was easier for people to use. This is the inner like circular part. We would have a hexagonal shape around this, but this is like what the inside would look like. So this pulls upward here and it comes off. And this part that pulls off with the handle here is kind of hard to see. We have a felt here to mimic the microfiber cloth, and we just have here to show where the spring energized seals would be. And then on the inside, we wanted to go with the technique used previously of having like a mesh on the inside, which we're mimicking here with like this wire frame. And we have two baseballs here to show how our prototype fits the samples here. And it can easily
Did you crochet that?
No, it's like one of
It's a
those
scouring
brushes,
pad.
yeah, a scouring pad that you use to like clean pots and pans. We were kind of like getting materials from everywhere for this project.
I like it.
just
I think
like-
that's really smart. Keep going.
And it would just fit back on and easily be able to close there.
Very nice. Okay, wait a minute. Before you walk away with that, so is there a locking mechanism that prevents it from coming apart, or is it just friction right now?
On this prototype, currently there is not a locking mechanism, but we're planning to add one. Um, we're planning to add one later, but for this cardboard prototype, we have nothing on here in terms of locking right now. But when we do further stages of it, we are going to add a lock mechanism, which we will talk about later.
Yeah,
Thank you.
we're gonna mention it.
Yes. Yeah. Okay. CAD. We threw together a CAD drawing because it better demonstrates everything. There's a video in there, but we also have it pulled up right here, so I can't go to the tab of the section
You
view.
might be able to hit OK on that.
Okay. So this is our design in CAD. I have a section view on this outer piece so that we can better see what's going on. But yes. So this would be that outer shell. It can slide out, and in here we have this orange piece represents where the microfiber would be. And then we have the spring energized seals, which would be a Teflon outer shell and either a steel or titanium spring on the inside. That's a materials decision that comes in later based on thermals and whatnot. And this pill-shaped object just represents the baseballs and the minimum space that would take up. We have about 1/2 inch of clearance on all sides for that steel mesh to provide cushioning that I didn't model, but would be there. And this would all slide on. Just a quick note on spring energized seals. The default we found in situations like this is to use O-rings, but in the Apollo missions, the O-ring ended up leaking because of the regolith. So in addition to having an O-ring on both the outside and inside, we have spring energized seals, which use spring force and Teflon to provide a gasket seal that can be used in piston-like situations and are used in various forms of industry. So that's something that we would add to add redundancy.
So I've never heard of those kind of seals. Glenn, have you?
I have not, but I'm open to find out about them.
Yeah, I
Yeah,
would love
we can
to.
talk more on it if you want a little bit more information. Inside it takes up a similar profile as an O-ring. It's a little bit larger in all dimensions. But how it works is if you see this little white sheathing, you have a Teflon or stiff plastic outer shell that goes all the way around what you're trying to seal. And you have surfaces that mate with the sliding faces. And on the inside, to provide an elastic force, you have a spring. So you can calibrate the amount of force that's applied on your sliding surface. You can calibrate the amount of force you need, and then also because it's an open gasket, you can have it set up so that if there is any leakage on the previous layer, that adds the spring force by going inside the gasket and ballooning out.
So
So,
is it supposed to keep the container with the balls airtight? Is that
Yes.
the purpose?
Yeah, so
Yes.
if there's any leakage on this initial O-ring, then it would have to go through 4 layers of spring energized seals. And the reason we went with these is we can use a much lower friction option for it to slide on. We initially planned on just using O-rings here, but based on some rough calculations, we need an insane amount of force to slide them on and maintain an airtight seal. So
Yes. And also
taking advantage-
temperature.
Yes.
The O-rings were responsible for one of our catastrophes, and that was
Yeah.
because the temperature in Florida went too cold for the O-rings. So are these temperature sensitive?
Yes, so that's something I've been looking into recently. I haven't gotten super specific on materials yet, but the plan is for the casing to be made of various alloys of titanium with a thermal coefficient of about 9 micrometers per meter degree Celsius. Teflon is about 14. So those do expand and contract more than the titanium within this temperature range. But the plan is that the springs would be made by a material that counteracts that. So we have adequate force going in both ways. And then also on this scale, we'd be looking at just a couple micrometers of movement. And with adequate spring force, we can counteract that to maintain an airtight seal.
Wow. Thank you for answering those questions. I really think that's unique. That's great research on your parts and design.
Now, I also see that you've got a ridge on the inside of the inside container at the very top. There you go. Tell me about that.
Yeah. So that's just the O-ring area to have that inner O-ring. It's not accurate in here. You would have something like a trapezoidal groove for the O-ring to sit in, and then compression and standard design practices for that. This is just to sort of visually demonstrate where it would be.
Okay. However, I do see that there's that orange portion on the top. Is that a gap? That's your O-ring there?
That's the O-ring, yeah.
Yeah. And actually, I like that you put it up there. It's going to minimize the chances of getting dirt on that. So I think that that's very smart. Good job, team.
All right. Moving past the video.
All right, so we talked about locking mechanisms a little bit. We were looking into bayonet locking mechanism, so you just push it down and turn it so that it stays in place. Which might be there are ways to incorporate the O-ring into that so that it is an airtight seal. So we're looking more into putting that in on our prototype. For storage, we were hoping to put grooves on the outside and use like wire ropes to hold it onto the side of the like the interior side of the ship.
Cable ties.
Cable ties, yeah. So we were also gonna ask if that would work. I looked a little bit into using cable ties on spaceships, but it wasn't very clear if we could use them for storage. So that is one question that I had.
No, I think those are a good possibility. I mean, whether you use ratchet straps or use some kind of a cable tie or things like that, these are all good options. And it's just a matter of, once you've got your suit off, you can use all kinds of things. And so it's not a requirement for you to have something planned out, but to have some options available is is a very good idea. Okay.
All right. Also, future plans is numbers, numbers, numbers. I need to do more work with the materials to get those dialed in. I mentioned the thermal coefficients. Geometry is a big thing. I don't want to run a finite element analysis, but external pressure is really difficult to calculate for. I've been down a rabbit hole of really long documents detailing the process for calculating materials for that. But that's another big thing. And then CAD, we naturally have to refine our CAD and start working on our final prototype. Those are our plans for the future.
Excellent. Okay. Is that your last slide?
There's one more, or two more.
Okay.
Alternate ideas. These are other things that we've been thinking of potentially incorporating. The first is, I don't know if you can tell, I'm a fan of material science. Electrodes. These are like magnets, but instead of holding a permanent magnetic charge, they hold a permanent electrostatic charge. And because dust or the regolith on the moon is generally charged and the mission is toward the south pole of the moon, where it tends to be negatively charged, we've been considering it. It needs more research, but we could have a plastic sheathing that has a permanent negative charge that would help repel any regolith from going onto the mating faces that produce the airtight seal. So that's one thing that we've briefly considered. More research needs to be done there. Another thing is shape memory alloys in helping with a seal or in being part of our actual container to help provide a better seal. And then also in the cushioning, perhaps instead of steel mesh, we use something like nitinol mesh that could, when brought inside the environment, the astronaut's environment, could potentially expand and seal around each object in a much more custom or encapsulating way than just having the steel mesh in there. That's another possibility. And then also maybe having a brush incorporated into our outer case so that when you pull it off, you can use that brush while you're out on the lunar environment to help brush off any dust from the mating face before you slide things back on. And then just as a joke we've thrown in there, if we had antimatter within our seals, any air that makes its way in would no longer be there.
Great idea.
Might be a little unfeasible. Might be a little
No.
unfeasible, but it's on there. And these are some questions we've had for you.
Yeah, to finish, we already went over storage a little bit, but we wanted to know like how big the astronauts' gloves are going to be, because we want to factor that in both to our handle and like how they're going to be able to like grip it or twist it. So do you have any information on like how big those are so we can try to model it and see what we need to change?
Sure. So imagine your fingers twice their diameter.
Okay.
Does that make sense?
Yeah.
And roughly how much added resistance will there be from the gloves?
Right. So, and that's a tough one to discuss, right? It's something you kind of have to experience. So imagine if you take a rubber glove and you put it into a box, okay? And then you take a vacuum cleaner and plug it into that box and turn it on. And what you're going to get is you're going to reduce that pressure in the glove box so that your glove actually inflates. Does that make sense?
Mhm.
And so as you're playing with that inflated glove, you're going to experience more of what that astronaut feels because the astronaut has about four psi, somewhere between 4 and 5 psi of air pressure in their suit. So whenever they're squeezing their hands, they're fighting against that 4 or 5 psi. Does that make sense?
So we've already talked a little bit about storage. You said just having some options is all right. To what extent should we account for manufacturability and other design processes in our prototype in CAD? Because currently it's set up so that it could be manufactured on a high precision lathe. But things like electrodes and whatnot might require more complicated internal geometries. So we naturally want it to be possible, but should we make it something that would be relatively easy to manufacture? Can we take advantage of more advanced manufacturing techniques?
Sure. Now, um, don't make it too complicated, right?
Okay.
So right now you've got a cylinder with a cap on it for both sides, and realistically, some of that could be made just by buying tubing at the correct dimensions, and then you just kind of weld on the top. Does that make sense?
Yeah.
And so these are options. Um, and see, so for example, your hexagonal outside, is that something where they can just make it on a lathe? Sure, sure. I mean, I think that is very much within the range of manufacturability. I think the bigger question is, how do you plan to represent your idea? How do you want to build it? I mean, are you going to 3D print? Are you going to continue with cardboard? How did you want to build it?
We were going to go down the 3D printing route.
And 3D printing works just fine for now, so I don't think that that's an issue.
Okay.
Um, let's see. Um, I really like that you're considering how do you want to store it on the spacecraft. Um, you know, so for example, oh, actually, let me ask you. You want a handle on it, and I think that's great. Is it going to be a rigid handle or is it going to be a soft handle? Is it going to be one that swivels down out of the way? How will that be affected by how you want to store it on the spacecraft?
We were probably thinking a more rigid handle because we were thinking with the locking mechanism, there would be a turning element involved. So we wanted them to be able to use the handle for ease of turning there, in case it was hard to grip with the gloves. We can definitely factor that into how we're going to be storing it.
Sure. And so there's plenty of options there for how you want to do that. And just consider, if I have if I have it as a rigid handle, can I still make it so that I can stack other ones on top of it? Or do I want them all to be something where, they all sit on the floor or in the bottom of a box or something like that? Okay.
Okay.
So can you go back to your previous slide? One or yeah, right there. Alternate ideals. So in manufacturability, right? You were asking about that. Are you thinking of doing any of these into your design or putting any of these alternate ideas into your design?
These are all things that we've seen potential in and not done enough research to feel comfortable including yet.
Okay.
Things like shape memory alloys, those would just be completely different materials. They wouldn't make manufacturability a big challenge. Really, it's just electrodes that they're touchy materials. They may not be as durable and might need more complex geometries to keep them secure.
Yeah. So you, so I actually like all three of these ideas, right? I even like the antimatter, but that's me. But for demonstrating, if you are going to do any of these, let's take the shape memory alloys. You don't have to, if they're expensive, you don't need to use them. Just use something that is similar, like foam, to do it. But it still would be valuable, I think, to research these ideas and tell NASA engineers about them. Does that make sense? And I
Yes.
and I like the idea of a brush. Hey, could they brush the the um the dust off? It's not so easy to brush dust off, because it kind of, with like static electricity, it sticks to things, right? But a brush might help some of it. We had a previous project of making a brush that could brush the dust off of stuff. So don't throw out. I would like you to research more on those ideas. I think they're awesome. Is what I'm trying to say. What do you think, Len?
Um, so in terms of brush, I think that that's also an interesting idea. Um, what kind of brush would you be looking at? I mean, is this a horsehair brush? Is this a Teflon brush or whatever? These are the kind of things you'd be thinking about. Um, in in terms of the electrics, I'm not so sure what kind of things you can do with that. Um, but I mean, do some research on it and see what's possible there. Um, in terms of shape memory alloys, I'm not opposed to them at all. I found them to be very interesting, but we're going through a lot of temperature swings, and I'm not sure if, could you have a problem where your shape memory alloy, it goes to one state because of being in a very low temperature, and then you bring it out into the sun and it goes into the other state because of being getting all hot. Explore what that can do. Okay.
Yep, thank you.
All
Okay.
right. Excellent job, team.
Did you have one more question we
You had
didn't
some more
answer?
questions in there. Yeah.
One more question. How exactly are we going to be testing the final prototype at the critical design review? Is there anything we should prioritize or focus on in terms of functionality for that?
Boy, that's a tough one, right? Because I'm not going to be able to stick it in some kind of a pressure vessel and start, see what happens there. I think that it's going to be a lot of look-see, right? Just looking to see how things are going.
Okay.
And especially if you do 3D printing with this, you can imagine that 3D printing is layering. And of course, those are not all perfect layers. And so getting it to seal, I think, would be very difficult. I think the answer is mostly we're going to be just looking at it. Now, one thought for you, you can imagine that. So when you package this up, your rocks up on the moon, you're going to then walk it inside where you're going to take it up to something like about 10 or 14 psi, 14.7 by the time it gets back to Earth. And so, what would be similar to going you know, from going from a vacuum to 1 psi or to 1 atmosphere? You know, if you wanted to test your box, you might swim it down to the bottom of the pool or something like that. And that might give you some ideas as to whether it's going to get, whether it's going to be able to hold the pressure. So these are just thoughts for you, but I don't think that we have a great way to be able to check them out since we're not going to be manufacturing them exactly the way we might for in preparation for going to the moon.
Okay.
So really what you have to become is a salesman for your product. Tell us all the advantages that you put into it and the research that you put into it, and why your project will work on the moon. Does that make sense?
Yes.
Okay.
And you mentioned that you wanted to have some kind of latches on the bottom. Did you want to tell us about your thoughts on the latches?
So we specifically were like what we had looked into so far was a bayonet locking
Oh, that's
mechanism.
it. Okay.
Yeah. So you just push it down and twist it.
Well, and so where did you want to put those bayonets? Are they going to be, I would guess that you'd put them at the very bottom. Is that right?
Yeah, we would be planning to put them like on the bottom rim
You
here.
can point at the.
Yeah, or either one. Like
Show me that again. Where did you
there's
want to?
so when you put this on, it would be at the bottom here, at like the gap here.
I see. Okay, I think that's a good idea. I like what you're thinking with that. Thank you very much.
And I like how the whole thing slips over the other thing. That's double insulation there. So that's pretty cool. That's a really good design. So Glenn, this is for you. Do they have to worry about radiation affecting their rocks?
Well, they've been sitting in radiation for 4.5 billion years. I don't know that we could do anything different with it. If anything, we'd be shielding it from some of the radiation.
So, but if they bring the samples into their habitat, would it be giving off radiation?
Oh, I see what you're saying. I don't think so. I mean, no more than them walking around outside. So I see your point. Just because they've been irradiated for 4.5 billion years.
Yeah.
I mean, could they be giving off some more radiation themselves? That's actually a great question. I don't think it's something that we can change other than with their container that they've got. So that's a good thought, Flo.
I'm just, we don't want to expose the astronauts in their habitat to any more radiation, and the container could protect against the radiation coming out.
Some of it could. I don't know enough about what kind of radiation we'd be expecting off of these rocks. That should be something that we would ask some of the geologists to find out what they think. Good question, Flo.
Yeah.
We can do some research into that as well and see about incorporating any necessary radiation shielding.
Yeah,
All right,
that
I
would
do
be
just
great.
want to switch gears too, just to allow my other team to come before the class. So great job on that. Thank you.
Thank you so
Good job,
much.
team. Keep this up.
Have
All
a
right, so
super
we're
day.
gonna have our trash ejector team come up and take you through their prototypes. So here they are.
Hello.
Hi, team. How are you doing?
Well,
Looks like, do you have 4 people in this? Is that right?
There's 2 sub teams. One has 6 people, the other has 4 people.
Yeah.
Excellent. Okay.
So our project was the trash ejector.
Grab the yep, go ahead.
And the problem that we had to consider was launching trash from the shuttle into space through some sort of disposal mechanism of our design. And in terms of the constraints that we had to consider for our design, we had the Campbell soup can as our the product that we were launching, and we had to build the stuff around that as well as the door to fit that constraint. The speed, it had to be less than 1 meter per second, so we had to take that into consideration. And the environment was the big thing because we're not dealing with stuff that's on Earth, we're dealing with space, vacuum, the extreme cold, a lot of stuff that we're not normally used to dealing with
in engineering, so a lot of different considerations we had to make there.
So we split into two sub-teams, as I mentioned. The first sub-team is the launch team, which had five members, and our goal was essentially to build the actual physical launch mechanism that would push out the trash from the spaceship. And we had to communicate with the other team effectively because we have to work around their constraints and their actual tubing and structure. So here's a sketch of our current design. We decided to go for a spring-powered mechanism, which would be a simple push-to-lock mechanism. So this is the spring mechanism when it's uncompressed, and this is the base plate which would attach onto the hatch, the inside of the hatch. And when you open the hatch, essentially you have access to this mechanism. And the way you would compress it is the astronaut would have to push the plate into it, and these two locking arms, they're powered by springs and they go inward. So when you push it down, there's a couple of notches where the locking arm would slide around the base plate, and when you let go, it would lock with the locking arms being like look at the next switch. The locking arms would be around the base plate and it would be locked in a compressed state. And essentially at this stage, you have the hatch open and the mechanism is compressed. So you would put the soup can in the actual structure, which is a pretty much like a tunnel, and you would put it in there and you would close the hatch and it's ready to be launched out of the spaceship. And to actually launch the mechanism, you would have a button which is attached to some linkages. These linkages would push out the notches on each side, which would essentially let go of the base plate and the spring would just push out. So it's connected to a spring because you want it to reset position. You don't want it to just stay there. So you push it, it launches it, and then it just resets because of the spring attached to it. So that's how the mechanism works.
Excellent.
Yeah, so we made some prototypes. We made a physical model, as you can see here on the right, and we also made a CAD model. And so the physical model we made using cardboard and some springs that we found around, and we hot glued. And so you can kind of see the idea of how you would push the top plate on the right image, and the two arms would kind of go around and lock it into place. On the left, you see the CAD model that we started. The locking mechanism itself, the two prongs on the right and left are actually inspired off of a mechanical pencil. And so we essentially were inspired by how that mechanism would lock, and we're trying to incorporate it here. We also have two springs that we're trying to use, and we're trying to get the best spring for this one using a website called McMaster so we can optimize for the speed. So we want to stay within that 1 meter per second speed limit. So yeah.
Very good.
All right. In the future, we want to make the spring compressible while the hatch is closed because we ran into a problem that when we would open the hatch, the springs wouldn't be able to clear. Like they need more clearance while opening the hatch, so we need to figure out that problem. We also wanted to reduce the amount of force needed to compress the spring because the astronauts should not have to apply a lot of force to close the mechanism. We also plan on adding rotation so that the can move out of the hatch smoother. And we'd also want to make the launcher usable with one hand so that the astronauts can hold on to something while compressing the spring.
Very good.
The alternate idea we had was pneumatics. Since we want to make sure like the inside of it is a vacuum, sucking out the air out with the air compressor, we can use that air we just sucked out and just put it into like a cylinder, which would then push into a piston and then put tension on the spring. And then once we want to release the spring, we can just release all the air out in that cylinder and then just launch the item or object.
So then the other team that we had was working on like the structure of the thing, which includes both doors, the inner and outer door, and also like things like shielding.
Okay.
So these are our basic sketches. We wanted to have an inner door that was domed, with the launch mechanism fitting inside of that to account for space concerns. This would also be a plug door, which we will explain a little more later. And here the can, which would be held in place by the launching mechanism is. And then our doors are also plug doors on the outside, which we're going to show a little more with our prototype. and they rotate from going curved inward to open like that. And there's going to be a circular like space in the center for the can to go through. So this is all like sized around the Campbell soup can here. So in terms of our prototype, we thought it would be easier just to like show you physically, because the pictures are a little hard to explain. So here we have the domed inner door, which we currently don't have like a locking mechanism on our prototype, but that's definitely something that we're going to add in the future. So currently the domed inner door would open, and would be like a plug door to keep it sealed, make sure it's sealed. And here we have our outer doors. This would be the side that faces outer space, and this is the inner side. They're curved here. So one pushes inward and creates that space, and then the other can push inward as well here. And there's that space in the middle that perfectly fits a Campbell soup can.
Very good. That's interesting.
And we would also have an O-ring around that on the outside.
Okay.
So our future plans are kind of regarding how do you lock the inner hatch? We were thinking just like a latching type thing with two O-rings just to create some sort of seal. For linkages, we weren't able to attach the linkage to the actual doors itself on the inside. Yeah, to the doors itself. That's just kind of what we thought for a basic linkage.
Bring that up closer to the camera if you would.
Yeah, sure. Just kind of what you were thinking on, is it reliable? Should we use that? Is there something else that we should use?
Okay. All right. No, keep going.
And then we just had some consideration when it comes to pressure calculations and material selections. That's a lot of K-shop too. So,
we just have to do the math, see what works best. Hinges and whatnot get complicated, especially in a pressure cycling environment. So we just need to look at what we're doing there. Haven't gotten super specific with that yet.
Okay.
Also, alternate ideas. So right now, our outer door is vastly different from every other design we've seen. All the other designs have a door that opens outwards in sort of the standard manner. The reason we went this way was our number one priority was redundancy. And with the current geometry, it acts like a plug door in that if there's ever a pressure leak on the inner door, the outer door physically stops any air from escaping. But in theory, we could also consider doing a standard external door. That's a completely different design, but that's an option. With that, one of the things on the slideshow was that if the space of the chamber was small enough, you wouldn't need to extract any air before launching. So another option is with that standard door, we use that trapped air in there to eject the can. That's not something we've looked into very much or talked about, but that's another option that we could consider. And then with the linkage, there's standard motor or linear rail actuation methods, but I like my shape memory alloys. We could look into using a shape memory alloy based linear actuator or rotational actuator to open and close those outer doors.
Okay. Very good. Okay.
Yes.
Wait.
So one of our earlier ideas for those outer doors was to just use magnets, electromagnets with attraction and repulsion until it's pressurized. That will keep the doors closed. Is there any interference we have to worry about if we pursue that design further?
I don't know about interference. So how do you think that you're going to use the magnets for the seal? I mean, I can see it as a mechanism for locking, but I'm not so sure that it makes a difference in terms of the seal. What do you think?
So the idea was that we would use the magnets to just close the doors initially, and then as it pressurizes, the seal gains force. And
Okay.
that sort of leads into that last question on the list. Is there an acceptable leak rate for those external doors? because I know there's an acceptable amount of air loss that you mentioned on the design slideshow. But the plan is to keep those external doors only pressurized when loading the trash, and otherwise that chamber would be a vacuum. So
Right.
is there acceptable leak rate when it's pressurized or?
I there's probably some kind of an acceptable leak rate, but I don't know that one. Obviously you'd want it to be very low,
Yes.
but is that in millitors per hour or something like that? I really don't know what they do. So I apologize. I don't know that one.
Okay.
Um,
We're a little out of time here, like our period. So, and some people have tests after this. So is there any advice that you could give to either team right now to help us improve our designs here?
Sure. So, for example, I like that you're doing the outer door as being one that closes from the it closes to increase the sealing rate, right? And I think that that's really smart. The difficulty is just how do you make it so that so that you can open it from the inside without having, and so consider if your axle if your pins for holding your door are consider them as axles. How would you rotate an axle to be able to open and close it, right? And so imagine if you put a gear on the top of your pin, now it becomes an axle, and now if I have another gear meshed with that, I can rotate and close that door any way that I want to. Does that make sense?
Yes.
So, and consider when I was a kid, we didn't have electric windows for the car. We would just hand crank. Is there any reason why we can't have hand crank for these doors, or do they have to be electric?
We could probably have something like that. We were just concerned about one, like how easy it would be for astronauts to use it. And also like vibration
Yeah.
or like
Maintain.
wear over time.
Sure.
Especially having a mechanical force transmitted to the outside of the vessel or an area that will be under vacuum. We were worried about maintaining durable seals that will last the lifetime of the mission.
Sure. And so none of our doors on the space station are electric. They're all mechanically driven. Okay. And including, so we have the windows on the cupola, and they all have shutters that open and close, and those are all done by hand crank as well. Okay. And so don't think that you have to go buy electric motors or anything. Doing a hand crank works just fine. Okay. Let's see. Oh, and I really like your idea with the locking mechanism for holding for releasing the can. Is there a way that you can make sure that just because I've opened the doors, my can is not going to start floating out, that it might have some kind of a lock mechanism? Does that make sense?
Could you repeat that real quick? Just one more time.
Sure. Okay, so you've put your can in, and you've opened the outer doors. What keeps my can from starting to float out before I push the button?
Great question. So I think one of the aspects we're thinking of, instead of initially we're thinking maybe a friction fit onto the plate, but then we realized maybe it's a little bit hard to actually close the hatch with that can already sticking out. So maybe there would be some sort of electromagnetic or magnetic force that's holding it in place so it doesn't move around. But we do have to think about ways to keep it in place because that's a pretty big concern.
Okay. And consider you've already got a mechanism that keeps your pusher plate from going forward until you push the button, right? Could you have another mechanism that operates that same way that holds your can inside?
Yeah.
And so I think that you've already got most of that mechanism, and you could just extend it to the opposite side of the pusher plate. I think you guys have a great idea, and I don't want to hold you up too much here. Excellent job, team. Keep this up. I think you got a really good design. Okay.
Thank you.
Thank you.
Yeah, I totally agree with Glenn. I like how it opens inside. So thank you so much.
No,
How are you
awesome. I appreciate your time, both of you, and the feedback. I think it was definitely a valuable experience for them to, hear their ideas out loud, and then to be able to get the feedback from both of you is critically important. So I appreciate that.
Excellent.
Now, anytime they have questions, just send it my way. And then I'll send it to Glenn. Thank you so much.
All right, no, that sounds great. And I think as our CAD models come along too, we can send those along and kind of get some more feedback before we head to the critical design review. I think that would be great.
Yeah, perfect. Thank you.
All right. Thank you so much. Have a great rest of the day.
You too. Bye-bye.
Thank you.
Bye.
All right, Flo. I'll see you later.
Yeah, not until 8 o'clock. I think 9 o'clock your time is
okay.
And then most of them today is with Nancy's.
Excellent.
Teams.
Okay.
We got a whole bunch. Harley's, Nancy's, Olympia. I made a mistake. Olympia had told me they were going on a field trip and to make it for today. So I forgot about that. So they're on our schedule for today, and Glenelg and Bozeman, and then all starting at 12:45 your time. It's East Troy. That's Nancy's.
Okay.
But
sounds good.
Thank you so much, Glenn. I appreciate it.
I'll talk to you soon.
Okay, bye-bye.
Bye-bye.